Hey kids, sorry for the delay. We'll start up here. So another problem for you. We're going to do two types of problems in this video. In this one, we're going to look at delta G from standard values. This is going to be a very straightforward, very easy calculation, just like we've done delta H from standards, delta S from standards. Delta G can be done from standards, going to tell us our spontaneity. These standard values that I have up on the screen, these were just pulled out of the appendix in the back of our book. Thermodynamic values are standards. They're published. I've got a set of them copied up on posted up on our Canvas page, easy to find, easy to use. And then the second problem we're going to do is another rehash from the past where we're going to use Hess's law with delta G instead of with delta H. So instead of calculating the enthalpy, we're going to calculate the free energy of this using Hess's law and rearranging some equations. First, let's do our standard values. As I say, equation is given to us, and these values are given to us. So to calculate delta G, this is really just simply of delta G of our reaction is going to be equal to delta G of our products. Just remember, it's always prod minus delta G react. Now, in this case, we have some coefficients coming into play, and we're going to make use of those. So with products, we're going to start with our CO2. So this is going to be equal to 3 moles. That's my coefficient for the CO2 times a negative 394 kilojoules per mole. So now when we multiply that out, that's going to clean up my moles. My moles are going to cancel. We're going to add that to the 4 moles of water, and water has a free energy value of negative 229 kilojoules per mole. And that's going to be my products minus my reactants over here, which are going to be a 1 mole times a negative 24 kilojoules per mole. And then, not that it matters, plus 5 moles times 0. That's why it doesn't matter. Products minus reactants. If we let TI do all the heavy lifting here, we're going to find out that our delta G value is negative 2074, and that's going to be in kilojoules because our moles have already canceled out. So what we have is something very free energy, exergonic is the word that's used with free energy. That's never going to come into play, but it's a good SAT word for you today, exergonic. So that's just a delta G from standard values. Now let's look at our second type of problem we want to do. And in this type of problem, we're going to use delta G from Hess's law, basically. Hess's law is a law of heat summation. And so in this case, it's not heat summation, it's free energy summation. So we're going to have to be given a fair amount of value. What the problem is going to read is calc delta G 4. And our target reaction is going to be very simple. We're going to take sulfur, add a little bit of oxygen, and that's going to make a little bit of sulfur dioxide, a little bit of SO2. Now, just to be perfectly correct and honest here, we do want to keep track. Sometimes our states of matter are going to come into play. In my experience, it's not really a commonality. Be aware of it. Watch out. We see it especially with H2O sometimes, but with our elements and our compounds here, nothing to. And so this is going to say, excuse me, given, and they're going to give us these two equations. S is a solid plus 3/2 O2 is a gas. Going to make a little bit of sulfur trioxide, also as a gas. That's going to have a delta G value of -371. A little free energy going on. That's in kilojoules. Okay, and they're also going to give us equation 2, which is 2 SO2s plus O2 is a gas. You see where that's going to come in and start to cancel out something. And now we have 2 SO3s. A lot of SO3s going on. The delta G on that, not quite as negative, but a -142 kilojoules. And so as we look at this, I'll scroll up a little bit, give myself a little bit of room. What I really have going on here is, here's my SO2. It's as a reactant, and I really need this to be a product, and I only need one of them. So I really feel like I'm going to reverse, give myself a little bit of space. I'm going to reverse that and multiply it by 1/2. Equation 1, I'm going to leave the same. I like that because equation 1 has my S right where I want it to stay. And so if I take this, I'm going to do my squiggly line. I'm going to rewrite both equations because that's what I do. S is a solid plus 3/2 O2. Excuse me. What the heck is going on there? 3/2 O2 is a gas, going to SO3 is a gas. That's going to be a -371. Reverse and cut in half that other equation. So now I have SO3. So that's going to cancel out quite nicely. Ba-bink to SO2 plus 1/2 of an O2. Get my states in there. Sorry, kids. And we reversed it and we halved it. So now positive 142 in half is a positive 71. Oh, look how that works out really pretty. Now let's just double check and make sure that our units, our equation is going to add up, because remember, it is a Hess's law problem. SO3 is going to cancel with SO3. And now 1/2 O2 is going to take a half off of that, 2/2 of O2. That's 2/2, 102, right? So now if we rewrite this, we get S as a solid plus O2 as a gas, makes a little bit of SO2 gas. And now if we add up -371, positive 71, we're going to get -300 kilojoules for delta G. So it's a real easy Hess's law. It's just we're doing it with free energy instead of doing it with enthalpy. The other problem we did, if we come in and we go back to review that, the other problem we did here is we did delta G by standards, products minus reactants. Two very straightforward, very easy problems for you. I'm Smath. I hope this video helped you.